Welcome to Night Shift Knowledge, a quiet place in the late hours where you can finally let go of the day. Take a moment to settle in, soften your shoulders, and allow the busy world to fade completely into the background. Tonight, we are going on a gentle journey through the fascinating corners of science, biology, and history. Before we begin, please know that the screen will fade to dark very soon. You can safely rest your eyes and leave this video playing as you drift off to sleep. I would also love to hear from you. Please leave a comment below with a general topic you would like me to cover in a future video. It is always a pleasure to read your ideas and shape this channel around what brings you peace. If you find comfort in this space, a like and a subscribe would be deeply appreciated. To ensure the next video quietly finds its way to you, please tap the notification bell. So as your breathing slows and your room grows a little darker, let your curiosity drift along with my voice. Let us begin. Imagine for a moment you are on a dive. The water is cool and the light is fading into a deep, serene blue. You're holding very still. And then you sense a presence. Not a fish, not a shark, something else entirely. It flows over the reef, a living liquid, its skin rippling with patterns of color and texture. It's an octopus, the common octopus. And as you watch this master of disguise, this intelligent explorer of the seabed, you are looking at a creature with 3 hearts, pumping blue blood. This is not science fiction. This is an animal that lives right here in our oceans. It has no bones. It can squeeze its body through a hole the size of its eyeball. It can solve puzzles, open jars, and change its appearance in a fraction of a second. And at the very core of its being, it runs on a system that seems utterly alien to us. 3 hearts, blue blood. Let's start with what you know, your own body. Put your hand on your chest. Feel that steady, rhythmic thump. That's your heart. 1 heart. A powerful 4-chambered pump made of muscle. It works tirelessly to send red, iron-rich blood through 60,000 miles of vessels in your body. That blood carries oxygen to every single cell, fueling everything you do. It's a system we share with every other mammal, bird, and reptile. It's the vertebrate way. It's our normal. Now picture the octopus again. Its normal is something else entirely. Inside its soft body, there isn't 1 pump. There are 3. 2 smaller hearts, 1 for each gill, push blood through those delicate fronds to grab oxygen from the water. Then 1 larger, more powerful heart takes that freshly oxygenated blood and sends it coursing out to the body, to the brain, to those 8 incredible arms. It's a dedicated delivery system, and the fluid it's pumping isn't red, it's a rich, royal blue. When it's oxygenated, it's the color of a deep summer sky. When the oxygen is depleted, it turns almost clear, a pale, ghostly bloom. This isn't a trick of the light. It's chemistry. Our blood is red because we use iron bound in a protein called hemoglobin to carry oxygen. Iron rusts red. The octopus uses copper. Its oxygen carrier is a protein called hemocyanin. Copper, when it binds with oxygen, turns blue. Think of the Statue of Liberty. That iconic green-blue hue is oxidized copper. Inside an octopus, that same basic reaction is the secret of its life. So here we have it, the central mystery waiting in the tide pools and the coral reefs and the shadowy depths. A creature of profound intelligence and beauty, built on a foundation that feels, to us, like it belongs in another world. A triple-hearted being with blue copper blood flowing through its veins. It makes you wonder, doesn't it? In the grand story of evolution, a story that gave us the elegant, efficient single heart, why would nature go down this path? Why build an animal with 3? It seems complicated. It seems extravagant. Perhaps even fragile. This isn't just a quirky fact. It's the key to understanding everything about this animal. Why it moves the way it does. Why it thinks the way it does. Why it lives a life of such breathtaking but brief bursts of activity. That blue blood and those 3 hearts are not just biological trivia. They are the engine of an alien intelligence right here on Earth. And over the next hour, we are going to follow that blue river inside to see how it shapes a life so different from our own. But first, we have to ask the obvious question. If 1 heart is good enough for a whale, for an eagle, for a human, why would evolution create 3 for an octopus? What problem was so great that it required this bizarre and beautiful solution? The answer begins not in the complexity of the present, but in a much simpler, more distant past. From simple shellfish, the evolutionary journey of a cephalopod. We've met our alien, an animal with 3 hearts and blood the color of the sea. It's a breathtaking piece of natural engineering. But it didn't just appear. Nothing in nature does. To understand why an octopus is built this way, we have to ask a much older question. Where did it come from? The answer is surprising. The ancestor of this sophisticated blue-blooded hunter was most likely something much simpler. Something like a snail or a clam. Picture a creature from 500 million years ago, a slow-moving mollusk grazing on the sea floor. It had a simple, open circulatory system. Its heart, just a single heart, pumped a fluid not quite blood into open cavities. It sloshed around its organs, delivering oxygen slowly before draining back. It was a low-pressure system for a low-energy life. No need for speed, no complex brain to fuel. This was the starting point. But evolution is a story of pressure and opportunity. In the ancient oceans, a new niche opened up. The water column was full of prey. But to take it, you needed to move. You needed to chase. You needed to become a predator. Some of those early mollusks made that leap. They became the first cephalopods. The name itself gives us a clue. Cephalopod means head-foot. Their muscular foot, the same organ a snail uses to crawl, was transformed. It became a set of grasping arms surrounding a central evolving brain. To propel this new body, they developed a form of jet propulsion. They would draw water into a cavity and then force it out through a funnel, shooting themselves backward. It was a revolutionary way to move. But this new lifestyle came with a huge metabolic demand. Jet propulsion is powerful, but it's not efficient. It burns energy fast, and that new, more complex brain is a hungry organ. All of this requires a massive amount of oxygen, far more than that old sloshing open circulatory system could ever deliver. So evolution engineered a major upgrade. The cephalopods developed one of the first truly closed circulatory systems in the invertebrate world. Instead of blood washing freely through cavities, it was now contained, locked inside a network of vessels, arteries, and veins. This created pressure. It turned a lazy stream into a focused, powerful flow. It was like going from a garden hose to a fire hose. This was the fundamental leap, the necessary foundation for everything that was to come. But here, the fossil record throws us a curveball. If we look for the ancestors of our soft, boneless octopus in the rocks, we mostly find shells. Beautiful spiral shells, the nautiloids, and later, the ammonites. They were the early champions of this cephalopod experiment. Their shells were buoyancy tanks, allowing them to master the open ocean. For hundreds of millions of years, they were the rulers of the seas. Our octopus lineage took a different path. It abandoned the shell. It traded that external armor for something else, muscle flexibility, intelligence. But soft tissue rots, it rarely fossilizes. So the story of the octopus's direct evolution is a ghost story, written in whispers and gaps in the rock. We know it happened, we can see the results, but the precise steps are hidden in deep time. We're left with the brilliant end product and a critical engineering problem. That new closed circulatory system was a success, but it had a flaw, a bottleneck. Think about the journey the blood now had to take. The systemic heart. The main heart pumps oxygen-rich blood out to the body, to the muscles, to the brain. That blood delivers its oxygen and becomes deoxygenated. It must then return to the heart to be sent out again. But it can't go directly back. It's loaded with carbon dioxide. It needs to visit the gills first, to offload that carbon dioxide and pick up a fresh supply of oxygen. And therein lay the problem. The gills of an octopus are dense, finely divided tissues. They're like a thick, resistant sponge. Pushing blood through them requires significant pressure. If the single systemic heart had to do all the work, pump blood through the high resistance of the gills and then through the entire rest of the body, it would be an immense strain. The pressure needed to push through the gills would be too high for the delicate vessels in the rest of the body. It was an evolutionary trade-off. Efficiency in one area created a weakness in another. Nature's solution was elegant. It was redundancy. It was a division of labor. Evolution didn't just strengthen the one heart, it added two more. It created a dedicated team. Two smaller hearts placed right at the entrance to each gill. We call them the branchial hearts. Their job is singular and crucial. They act as boosters. They take the returning deoxygenated blood and give it the powerful push it needs to force its way through the dense network of the gills. Once the blood is through the gills, now freshly oxygenated and blue, it flows smoothly into the systemic heart. That main heart is now free to do its own job perfectly, to take that refreshed blood and pump it out to the body with strong, clean pressure. No bottleneck, no overwhelming strain. So the three-heart system wasn't a random extravagance. It was the necessary fix for a brilliant but flawed design. It was the evolutionary workaround that allowed the closed circulatory system to function under the demands of an active, intelligent, predatory life. It was the answer to a question posed by a half-billion-year-old gamble. The gamble of leaving the seafloor, abandoning the shell, and becoming something entirely new. The ghost in the rocks found its solution. And that solution beats 3 times over in the alien we met in the deep blue. So we've traced the path from a simple mollusk to this sophisticated hunter. It's a story of pressure, opportunity, and radical anatomical reinvention. That reinvention produced one of the ocean's most astonishing engines. An engine that runs on blue blood and needs 3 separate hearts to keep it alive. Consider the inner world of an octopus. It's a soft, boneless body. But inside, there's a network of highways and pumping stations working in perfect rhythm. This system powers every thought and every movement. It's the triple heart engine. Let's start with the hearts themselves. There are 3. 2 are called the branchial hearts. Think of them as the first stage of a rocket. Their job is singular and absolutely critical. They pump blood to the gills. That's it. They sit right at the base of those 2 feathery gills. With every beat, they send a rush of blood into the delicate tissues where oxygen is absorbed from the water. That blood, freshly oxygenated and blue, then flows to the 3rd heart. This is the main event, the systemic heart. It's the central pump, the one that sends life to every corner of the body, to to the brain, to the arms, to all the organs. It's the engine that drives the animal forward. But here's the catch. The systemic heart has a critical weakness. A built-in limitation. It stops. When the octopus needs to swim, to jet away from a predator, to exert itself with intense effort, that main heart simply stops beating. It goes quiet. For a creature that seems so fluid and powerful, this is a profound metabolic bottleneck. Let's walk through the whole loop. The full journey of a single drop of that blue blood. It begins its circuit depleted of oxygen. It's spent. It flows back from the body, returning to the branchial hearts. These two pumps kick in. They pressurize the blood and send it on a short, vital trip through the gills. Think of the gills as a busy exchange office. Here, in the thin membranes, carbon dioxide is released into the water, and fresh oxygen is picked up. The copper in the blood's special protein, hemocyanin, binds to the oxygen. That binding turns the blood a vibrant, deep blue. Now, recharged and blue, the blood doesn't go straight to the body. It can't. The pressure is too low after passing through the gills, so it flows into a waiting chamber, the systemic heart. This central pump now has its fuel. It contracts powerfully, sending this oxygen-rich blue blood surging through a network of arteries and vessels. Out to the brain, a hungry organ. Down the length of each powerful arm, to the digestive gland, the kidneys, everywhere. The blood delivers its precious oxygen cargo. It feeds the cells. In return, it picks up the waste product, carbon dioxide. Now blue, but deoxygenated, it begins the return trip. Draining back through the veins. Back to the starting line. Back to those two branchial hearts. And the cycle begins again. So you have this beautifully coordinated system, two hearts for the gills. One heart for the body. It's a closed loop of vessels, which is actually quite advanced for a mollusk. It's a high-pressure system designed to deliver oxygen quickly to demanding tissues. But that design has a trade-off, a compromise. The systemic heart, the main pump, depends entirely on the branchial hearts doing their job perfectly. It needs that oxygen-rich blood from the gills to even function, and during a sprint, everything falls apart. Think of the octopus deciding to flee. It fills its mantle cavity with water. Then it contracts its muscles violently, shooting itself backwards in a jet of water. It's a burst of incredible speed. But that muscular contraction squeezes the very veins that are trying to return blood to the hearts. The return flow is choked off. With no blood returning, the systemic heart has nothing to pump. So it stops. It simply waits. The octopus is now running on a kind of physiological credit. On the oxygen already in its tissues and blood. It's an all-or-nothing sprint, and it can only last for a few moments. After that, the animal must stop. It must rest. It must let its circulatory system catch up. The main heart starts beating again, and the slow, steady process of recovery begins. It's an engine built for bursts, not marathons. The branchial hearts are like dedicated superchargers, forcing fuel into the system. The systemic heart is the high-performance main engine. But it's fragile. It stalls under the heaviest load. This explains so much about an octopus's life. Why it's a patient ambush predator, not a relentless chaser. Why it prefers to crawl and explore rather than swim. Swimming is expensive. It's a crisis for its circulatory system. So we have this marvel of engineering. A 3-heart pump that powers one of the most intelligent invertebrates on the planet. But it runs on a strange fuel. A fuel that's blue, not red. A fuel based on copper, not iron. And that choice of fuel is everything. It's the reason for the blue blood. It's the reason the system works the way it does. It's the reason for both its brilliance and its limitation. Why would evolution choose copper? In a world dominated by iron-based blood, why go blue? That's the chemical mystery at the core of this creature, the story of its unique life fluid. So we've just mapped the plumbing. The two branchial hearts, the single powerful systemic heart, the closed loop of veins and arteries. It's a brilliant, intricate engine. But what fuels it? What is this life fluid, this strange blue blood coursing through those vessels? The answer isn't just about color, it's about chemistry. A fundamental choice made deep in evolutionary time. A choice between two metals. We vertebrates, we mammals, we chose iron. Our blood is red because of hemoglobin. It's a protein with an iron atom at its core. When that iron grabs an oxygen molecule, it turns a bright, rusty red. That's the color of life for us. But the octopus, it chose copper. Its oxygen carrier is called hemocyanin. Hemos for blood, cyanin for blue. And when the copper atoms in hemocyanin bind with oxygen, they don't turn red. They turn a deep, vivid cerulean blue. It's the same reason the Statue of Liberty is green. That's copper aging and oxidizing. In the octopus, that blue is not a sign of age, it's a sign of life in every beat of its three hearts. This is more than a color swap, it's a completely different design philosophy. In our bodies, hemoglobin is packed neatly inside red blood cells. Trillions of little delivery trucks carrying their iron cargo. Hemocyanin is a free agent. It's dissolved directly into the blood plasma, swimming freely in the liquid. No cells, no packaging. It's just there. This has consequences. For one, it's generally less efficient. Hemocyanin just doesn't hold onto oxygen as tightly as hemoglobin does, especially when things get warm. In warm water, hemocyanin gets clumsy. It's more likely to drop its precious oxygen cargo before it reaches the tissues that need it. This is a core reason why the octopus is not a marathon runner. Its fuel is less potent. Its system, for all its three-heart complexity, can't sustain a high metabolic rate for long. The systemic heart, that main pump to the body, actually shuts down when the animal swims hard. It can't keep up. So the octopus relies on power, on explosive short bursts. Then it must rest, panting, letting its branchial heart slowly recharge the system with what oxygen it can gather. But here's the beautiful counterintuitive twist. In the grand trade-off of evolution, this less efficient system has a spectacular advantage. Hemocyanin performs better in the cold, in low oxygen environments. Where the water is icy and oxygen is scarce, that's where copper-based blood comes into its own. It's more willing to pick up oxygen in those harsh conditions. This isn't a flaw. It's a specialization, a key that unlocked the deep, cold waters of the world for the cephalopods. While many creatures are locked out, the squid, the octopus, the cuttlefish, their blue blood lets them in. There's another more delicate property of this copper-based life fluid. It's exquisitely sensitive to its chemical surroundings, specifically to acidity. Imagine hemocyanin as a diligent courier carrying a parcel of oxygen. The parcel is held by a delicate chemical handshake. Now, make the environment even slightly more acidic. Add just a few extra hydrogen ions to the blood. That handshake weakens. The courier's grip fails. It drops the parcel. The oxygen is lost. For an octopus, even a small shift in the pH of its blood, a tiny increase in acidity, can cause hemocyanin to simply let go. This is a system that demands balance, a precise chemical harmony. And this brings us to the true nature of the octopus's world, a world built not on stamina, but on strategy. not on endurance, but on brilliance. Its blue blood, for all its marvels, is a demanding fuel. It requires cold, oxygen-rich water. It requires a stable, balanced chemistry. It's a high-performance fluid for a high-performance creature, but with a very narrow operating window. So, the octopus adapted its life to this reality. It became a master of the short, decisive engagement, a sprinter in a world of potential marathoners. It uses its incredible intelligence to avoid long chases, to set ambushes, to solve problems with its mind rather than its muscles, to compress its most demanding activities into brief, dazzling bursts of power and color. Its famous camouflage, its jet-propelled escape, its intricate manipulation of objects, all of these are powered by that blue, copper-rich blood. And all of them come with a metabolic price tag, a debt that must be paid in rest and recovery. The creature with 3 hearts is not built for the long haul. It's built for the perfect moment, the sudden, decisive strike, the brilliant flash of insight. Then a retreat into the den, hearts beating, gills pulsing, slowly washing that unique, beautiful blue blood with fresh oxygen, waiting for the next opportunity to explode into action. Its blood is not red, it's blue. And that color tells the story of its life, a life of magnificent, fragile bursts. So we have the engine, and we have the fuel. That remarkable copper-based blue blood. But what does it mean to live with this system? To be an animal that runs on bursts, not endurance? Picture an octopus in its world. It moves with a slow, deliberate grace. Its skin ripples with colors and textures. It's a master of stillness and patience. Then a threat appears, a predator. In an instant, that stillness vanishes. You hear a powerful whoosh of water. The octopus compresses its mantle and jets backward. It's a blur, a rocket. It can reach astonishing speed in a fraction of a second. But then it stops. Just a few body lengths away, it lands on the bottom and seems to just rest. Its mantle pulses slowly. For a moment, it's almost vulnerable. That pause isn't a choice. It's a physiological necessity. Remember the systemic heart, the main pump for the body. During that explosive jetting, it actually stops beating. The 2 branchial hearts, the ones that push blood through the gills, they keep working. But the central pump takes a break, so the octopus sprinted on borrowed oxygen. Now it has to recover. Its systemic heart restarts. It pumps that blue oxygen-rich blood to its tired muscles. It's catching its breath. In the world of the octopus, every sprint has a tax, and it must be paid immediately. This is the central constraint of its life, a life of bursts. It cannot chase down prey for miles. It cannot engage in a long, drawn-out battle. Its brilliant circulatory system, with its 3 hearts and copper-based blood, simply isn't built for that. It's built for power, not stamina. So, evolution shaped a different kind of hunter, an ambush predator, a genius of stealth. Since it can't win with endurance, it wins with deception. With camouflage so precise, it seems like magic. With the ability to squeeze into impossibly small cracks. It plans. It waits. It calculates the perfect moment for that one explosive strike. This leads us to a fascinating idea, a compelling evolutionary question. Did this physical limitation actually drive the evolution of its famous intelligence? Think about it. If you can't overpower every problem, you have to outsmart them. If you can't run away from every threat, you have to hide or trick your way out. An octopus encounters a jar with a tasty crab inside. It can't just smash the jar with brute force. Its muscles fatigue too quickly. So it learns. It experiments. It uses its flexible arms to feel for a weakness, to twist a lid, to solve the puzzle. Its intelligence becomes its primary tool for survival. And that intelligence is unlike ours. It's not centralized in one big brain. Roughly 2/3 of an octopus's neurons aren't in its head, they're in its arms. Each arm has a kind of mini-brain. It can taste, it can touch, it can make basic decisions on its own. An arm can continue exploring even if it's been severed from the body. This is a distributed intelligence. A thinking, feeling network. Now consider the blood supply that supports this. Each of those 8 powerful, intelligent arms needs a robust flow of oxygen and nutrients. The complex, high-pressure circulatory system we've been describing delivers that blue blood directly into a vast network of vessels throughout the arm. It fuels not just muscle, but neural tissue. It supports a body where thought and action are deeply intertwined at their fingertips. This connection between physiology and capability is so intimate, it even dictates how we care for them. Veterinarians performing surgery on an octopus face a unique challenge. They can't just put the whole animal under and focus on the operation. They must always keep the octopus's gills immersed in water. Why? Because if the gills dry out, the branchial hearts can't function. If those 2 hearts fail, the systemic heart gets no oxygenated blood. The entire triple heart engine seizes up. So even on the operating table, the octopus's life depends on the constant rhythmic work of those 2 gill-bound pumps. It's a system of breathtaking elegance and precision, engineered by millions of years of evolution for a specific life in a specific world. A life of patience, of bursts of genius, of solving physical problems with mental prowess. But this brilliant system, this finely tuned marvel of copper and muscle, has a critical vulnerability, a flaw in its design that was never a problem in the ancient ocean, but is becoming a deadly threat in ours. That flaw lies in the very chemistry of its blue blood. And then it tires. The rocket engine sputters. That brilliant burst of speed, powered by its 3 hearts and blue blood, is over in seconds. The octopus settles. Its main heart resumes its beat. It finds a crevice, and its skin settles back into a complex pattern. It breathes. It rests. This is the rhythm of a life built on bursts, a rhythm perfected over hundreds of millions of years. A rhythm that has allowed this soft-bodied, blue-blooded creature to thrive in almost every ocean on Earth. But that rhythm is changing. The ocean itself is changing. And the very chemistry that makes the octopus's life possible, that blue copper-based blood, is facing a threat it never evolved to handle. For all its brilliance, the octopus circulatory system is a precise machine, fine-tuned to a specific world, a world with a certain temperature and a certain acidity. We are altering that world. And the creature with 3 hearts may be uniquely vulnerable. The first threat comes from an invisible gas, carbon dioxide. When we burn fossil fuels, we release CO2 into the atmosphere. A lot of it gets absorbed by the oceans. When carbon dioxide dissolves in seawater, it forms carbonic acid. This process is called ocean acidification. It's making the entire ocean more acidic, lowering its pH. For us, with our iron-based hemoglobin safe inside red blood cells, this shift might seem abstract. For an octopus, it's a direct attack on its lifeblood. Remember hemocyanin, that remarkable copper protein floating free in its blood. Hemocyanin's ability to grab oxygen molecules is exquisitely sensitive to the pH around it. In more acidic water, the blood becomes more acidic too. In that environment, hemocyanin struggles. Its grip on oxygen weakens. It's like the fuel is being watered down. The octopus's blood can't carry as much oxygen even if there's plenty in the water. So one heart of the problem is acidification, crippling the blood's capacity. The other is warming. The ocean is getting hotter. Warm water holds less dissolved oxygen. There's simply less fuel available. But that's not all. Heat is a double-edged sword. As the water warms, the octopus's metabolism speeds up. Its cells demand more oxygen, not less. It needs to breathe more. Its hearts need to work harder. Yet, at the same time, hemocyanin becomes less efficient at higher temperatures. It's a cruel paradox. The animal needs more oxygen, but its blood is worse at picking it up, and the water has less to offer. Imagine running a marathon, but someone slowly tightening a belt around your chest. And the air is getting thinner. That's the challenge we're creating for these animals. Scientific studies paint a concerning picture. Research on various cephalopods, from squids to cuttlefish, shows that under the combined stress of warming and acidification, their circulatory systems are pushed to the brink. Heart rates become erratic. Growth is stunted. The time they can spend actively hunting or escaping plummets. Their world of bursts becomes a world of shorter, more desperate bursts, with longer, more dangerous recoveries. This isn't just about physiology. It's about survival. An octopus that tires too quickly becomes a meal. A predator that can't chase its prey will starve. The delicate balance of its entire existence is being tilted. The octopus represents something profound. It's not just another animal. It's an entire other way to build a complex, intelligent, conscious being. While our ancestors were evolving spines and red blood, theirs were losing their shells and embracing copper. They found a different path to sophistication. A path that led to camouflage, problem-solving, and curiosity. They are, in the truest sense, aliens on our own planet. A testament to life's relentless, creative ingenuity. For hundreds of millions of years, this alternative blueprint worked. It conquered the oceans. It produced masters of disguise and escape artists. Its success is written in the very blue of its blood. But now, its future is written in something else. In the rising concentration of carbon dioxide. In the incremental warming of a degree per decade. The age of humans is testing this ancient marvel in a way no previous epoch ever did. The creature with 3 hearts and blue blood is a fragile marvel. Its incredible adaptation is also its Achilles heel. Its success is bound to the stability of the sea. So picture this one last time. Not a burst of speed, but a moment of quiet. In the dappled light of a reef, an octopus rests in its den. Its body pulses gently with each breath. Its 3 hearts beat a steady, coordinated rhythm, pumping that miraculous blue fluid through its veins. It is a symbol of profound adaptation, a wonder of evolution. But listen to the water around it. It is telling a different story. A story of change. A story of a world altering faster than this ancient rhythm can adjust. The octopus's future, the future of this entire other branch of intelligent life, now hinges on our actions. On what we do to its home, the vast, changing, and vulnerable ocean. We have reached the end of tonight's topics, and it is time to let your mind completely unwind. Whatever you learned tonight, let it fade into a soft hum as you drift off. Thank you for being a part of Night Shift Knowledge and sharing this quiet space with me. Remember to leave a topic suggestion for next time if you are still awake, but for now, just rest. Sleep well, and I will be here the next time you need to quiet your mind. Good night.